Okay, so this is a strengths problem, and we are looking at composite behavior. So we have two or more materials in our beam, and if it tells us it's composite, then we have to accept that there's full bonding that takes place between the two materials, so they are acting in unison versus both carrying their own set of loading. So we have a simply supported beam, composite, that is 5 meters long. It carries a uniform load. The beam is constructed of southern pine, so we have our modulus of elasticity. We have the dimensions of the beam, and we have a reinforcement on the bottom of steel, and its modulus and its dimensions, and we want to determine the maximum bending stresses produced in the timber and the steel given W. Then we want to sketch it, and then we want to assume that we have allowable stresses and go back and determine, do we have the maximum W on here or not. So just like every single problem that we're going to do when we look at beams, whether it's bending or shear, is typically we're going to have to start with finding reactions, drawing a shear and moment diagram, looking at section properties. So 3 is section properties. And that is all before I can come into looking at my bending stress due to moment. So moment is going to come from the reactions in the shear and moment diagram. My I is going to come from my section properties, and Y will also come from my section properties. Because I have two materials, I'm going to have to transform. I'm going to have to transform this into one material. So I'm going to start with reactions. If it's a simply supported beam and it's symmetric, and W equals 12 kilonewtons per meter, that's going to be 12 times 10 to the third newtons per meter. Remember, I like to have everything in newtons and meters. And so I know that it's going to be equally split between A and B. So the area is base. So area equals base times height, and that will give us the total like point load that would go in the middle. So we have 5, enter, 12 e to the third times, which is 60,000 newtons. And then if I divide that by 2, this is going to be 30,000 newtons and 30,000 newtons. So now if I draw a shear moment diagram, it should be pretty easy to draw. So I can see my maximum shear is going to be up here at 30,000 and come down here, and we'll have that peak right there in the middle. So when I draw my moment diagram, positive, negative, that means my slope is going down, my slope is going up with the peak right here. And this is going to be 1/2 base times height. So again, we're looking at the area, 1/2 base times height. So I have 1/2. My base of this triangle is 2.5 meters, and my height is 30,000 newtons. So I have 30,000, 2.5 times 2 divided by, and I get a moment max of 37,500 Newton meters. And that's going to occur right here in the center of the beam. This is a positive moment, so when I see positive moment, I know that I have compression tension in terms of distribution. Okay, so we've done reactions, we've done our shear moment diagram, now we need to look at section properties. And when we have two materials, we have to transform into one material. So we're going to transform the steel into wood. So when I look at that modular ratio, I'm going to transform the steel into the wood. So what we're transforming goes on top, what we're transforming into goes to bottom. So when I go back and look at my steel, it's 200 gigapascals, and I'm going to leave the gigapascals off because they both have the same units. And when I look at the modulus for my wood, it is 12 gigapascals. So we can see that that aluminum is, or that steel is much, much, much stiffer in terms of behavior. So we should have 200 enter, and then 12 divided by. So we have a modular ratio of 6.67. And that means our new base of steel equals N times the original. So we have 16.67 times. And this plate, if we look right here at the plate, it says that the plate is 150 So that's 150 millimeters, which is 0.15 meters. So I have 0.15 meters is my original. And when I multiply that out, 0.15 times, I get 2.5 meters, which is really, really wide when you think about this being on the base of the beam. But it's that much stiffer than the wood, which you can see by that ratio. Okay, so we now need to, when we have a new section, we have to just forget that this is rectangular looking, and we are going to draw our new cross section, and we can see that this is 0.36 meters tall. Okay, and it has a width of 0.2 meters. And then we have this section on the bottom, which is really, really long and skinny. In fact, it's 2.5 meters long. We are not changing the height. I have to go back up. Okay, so its height is still 0.012 meters tall. Okay, if we were bending about a different axis, we would have to change the widths this way, but we're just doing bending about the main kind of axis like that. So let's start at the bottom, and y bar equals the sum of a y tildes over the sum of a's. And if you're struggling with this, you need to go back and watch a statics video. And I'm going to start at the bottom. So my area is 2.5 meters times 0.012 meters. And then my tilde from the bottom here for my global is 0.012 over 2 plus, okay, this area. So I have 0.2 times 0.36. And we have to march up 0.012. And then to get to the centroid, it's 0.36 divided by 2. And all of this over the area of 2.5 times 0.012 plus 0.2 times 0.36. So let's figure out what we have. 2.5, 0.012 times 0.12, 2 divided by, times, and then 0.2, enter, 0.36 times, 0.012, enter, 0.36, enter, 2 divided by, plus, times, plus 2.5, 0.012 times, 0.2, 0.36 times, plus, and divided by. And I get a y bar of 0.137 inches going up. So it's going to be, if this is 0.012, we're kind of up, kind of like where I drew it, kind of right up there. Okay, so now we have to find moment of inertia, and we're going to be finding it about that centroidal axis. So if this is 0.137, then I need to figure out the centroid here, because I'm going to sum my eyes about their own, okay, their own centroids, plus neither of these centroids lie on the centroid of the whole, so I'm going to have to include that 80 squared. And that 80 squared term is from the centroid of the whole to the centroid of the piece. So both of these are rectangles, so we're going to be using BH cubed over 12. So the base of 2.5, 0.012 cubed over 12 plus 2.5 times 0.012, that's my area. And then 0.137 minus 0.012 over 2 squared. So that'll give us the moment of inertia of this bottom piece with respect to the whole, plus, okay, base 0.2, height 0.23 or 0.36 cubed over 12 plus base height. So this is my area. And then we have 0.137 minus, okay, and here's our value from the global to the centroid of that top piece. So minus 0.012 plus 0.36 over 2 squared. So I hope you guys can see that. I need like a real studio. So multiply 2.5, enter, 0.012 to the cubed, times 12 divided by 2.5, enter, 0.012 times 0.137, enter, 0.012, 2 divided by, minus, squared, times, plus. So these numbers look really, really small because we are working in meters. I turned everything into meters because our stresses, remember, is in gigapascal, which is a Newton per meter squared. So we're going to have a very, very tiny number. Conversely, if we left it in millimeters, because it's to the fourth, we would have had a ginormous number. So that's why it looks so small. I prefer inches and feet and pounds and kips because the numbers make more sense to me. So 0.2 enter, 0.36 enter to the third, times 12 divided by, and then I have 0.2, 0.36 times 0.137 enter, 0.012 enter, 0.36 2 divided by, plus, minus, squared, times, plus, plus. So I get 0.00151 meters to the fourth, and that's my I transformed. Okay, so now that we have that done, this is the hard part. We have our section properties done. We can start working on our stress. So I've got a clean sheet of paper here, and we're just going to summarize. Our maximum moment is 37,500 Newton meters, and it's positive, so compression tension. And I have a Y bar of 0.137 inches up from the bottom, and I have an I transformed of 0.00151 meters to the fourth. I don't know why I said inches, that should be meters. And then, okay, I have a transformation of 16.667, and that is going from steel into wood. So we have to make sure that we take that back out as we're doing our stresses. So let's draw a pretty big little picture here so we can sketch out our stress distribution. And no, it's not drawn to scale because I don't have enough room for that piece. So the centroid is kind of like right here. Okay, and then I'm just going to draw the top over, my transition, the bottom over, and I know that I'm working with stress. And I'm going to guess that we're going to be in gigapascals, which is Newton meter times 10 to the 6th. I know that we have compression on the top, and I like to just go ahead and draw my compression to the left, like it's negative, because I'm going to show that we're getting shorter. Okay, and we're going to come through here, pretend that that hit right there on 0, and then I know that we're going to have a jump where we change materials. Okay, so I know what this is going to look like before we get started, but we're actually going to find all of our numbers to fill this in. So when I'm looking at the wood, that's the original material, I can use my over I. And here we are looking at, actually the maximum, it's C. So C is going to be from the centroid to the outermost fiber. So that's going to be C to the top. When I'm looking at the piece of wood here, so this is all in compression, this is in tension, this piece down here that's in tension, I now have, okay, I now have this, it's a Y, and it's going to go from the centroid just to that area of where we're changing materials. When I want to go all the way to the bottom, okay, all the way to the bottom, that's going to be our C to the bottom, and that equals Y bar that we found. So let's look at the wood first, and let's do the top, which is in compression. So stress equals MC over I. So I have 37,500 Newton meters, okay, times, the whole thing is 0.36 plus 0.012. So that is the entire height, okay, the entire height minus Y bar, and that's my Y bar, which was 0.137 meters. So that gets me this distance up here to the top, divided by 0.00151 meters to the fourth. Okay, so we have 37,500, enter, check. Whoops, I don't want to space, 0.36, 0.012 plus, that's my entire height, minus 0.137, that's my Y bar from the bottom. Okay, So 0.235, if I wanted to know, that would be y bar to the top. So y bar to the top is 0.235. Y bar to the bottom was 0.137. I'm going to multiply those and divide by 0.151 divided by, and I get this rather large number. But remember, this is in Newton per meter squared. So we're going to go over 1, 2, 3, 4, 5, 6. So my stress at the top, when I'm looking at the wood, is 5.84. Okay, and we moved it over times 10 to the 6, so gigapascals. Or you could call it 5.84 times 10 to the, actually that's mega. I got carried away with how much I was moving things. Okay, so that means if we've been looking at stresses as gigapascals and we're only in megapascals, we have a lot more capacity in this beam than the load that we're putting on it. So megapascals, so that's times 10 to the 6th Newton per meter squared. So this point right here, if I'm going to put stress in megapascals, that's my units. Then up here at the top, I'm in compression, so negative 5.84. And I could actually call this, yeah, megapascals. And this is negative because we're in compression. I know it's going to be linear as I move down this length, my y, down, until I'm right here at the centroid. And if I put a 0 in at my centroid, I find that indeed my stress here is 0. And so now we're going to work our way into the tensile zone. So if I'm looking at the bottom fiber of my timber, okay, so we're looking at the bottom fiber of my timber, it's in tension. It has the same moment of 37,500 Newton meters, but this time we're not going up to the top, we're not going all the way to the bottom, we are just going to that transition zone. So it's 0.137, that's my y bar minus, and then the thickness of this is 0.012. So this distance right here is from the centroid to that interface. Okay, and then we're going to divide by, it's the same moment of inertia. So I get 37,500, 0.137, 0.012 minus, times, so it's 0.125 meters, okay, 0.125 meters from the centroid to the transition. So times, and then I have 0.00151 divided by, and then I'm going to move it over 1, 2, 3, 4, 5, 6. So we are at 3.1 times 10 to the 6th Newton per meter squared, which is a megapascal. So I know this value is 3.1. Okay, so now I need to find at that same y, well, what is the steel? What kind of stress is the steel under? So it's at the same distance, they have the same moment, they have the same y, they have the same moment of inertia. So now when I'm looking at the steel, which is going to be the top of the steel, we are still in tension. It is going to be the stress that we found in the wood, okay, the stress we found in the wood times N. Or you could rewrite it. You could put 37,500 times, it's still that same y distance, 0.137 minus 0.012 divided by, but I know it's the same equation. So I can take this 3.1. So I have 16.67 times 3.1 times 10 to the 6th, and 16.666667 times, okay, I get this value. I'm going to move it over 1, 2, 3, 4, 5, 6, and now my stress is 51.7 megapascals, okay, which is quite a bit larger than what I had in the wood, but it's that modular ratio, okay. So when I come back up here to my picture, I know that my stress is 51.7 megapascals at that point, and now I know the maximum is going to be all the way down at y bar, okay, y bar, because that's my maximum distance from the centroid to the bottom. So let's look at the steel. We're going to look at the bottom of the steel, which is still in tension because we're in the tension region, and our stress equals Nm, that should be an N, Nmy over I. So I have 16.67 times 37,500 times, okay, y bar to the bottom was 0.137 meters down, divided by 0.00151 meters to the fourth. All of my units are correct. So I have 16.67, 37,500 times 0.137 times 0.00151 divided by 1, 2, 3, 4, 5, 6. And I get that my stress is 56.7 megapascals. It doesn't look like it's a whole lot more, but remember, it's a very, very, very thin piece. Okay, so I can come back over here and I have 56.7 megapascals. So, again, I want you all to remember that as I take this beam and I put it into bending, and I look at the cross section, okay, I look at the cross section. If I were to look at the strain, okay, my strain, which is change in length per unit length, my strain is going to be a constant, okay, compression to tension. There's not going to be a jag in it. But because right here I have two different materials at this same piece, remember that when we have a stress strain curve, both of these are going to have unique values of E. Our modulus of elasticity is different. So I have one strain, okay, and then I'm going to go back and see, okay, I actually have two stresses. Here's my wood and here's my steel, okay? And now that we know what the stress is, like if I wanted to know, well, what is the strain? I actually know the stress right up here at the top. I calculated it was negative 5.84. I also know the modulus of elasticity for wood. It was given as 12 gigapascals. So we could actually go back and calculate this value of strain. How much shortening is happening? How much elongation is happening? How much elongation is happening? The strain's the same, but we do have a different stress. Okay, so I know there's more to this problem, but I'm going to stop this problem right now because it's already 22 minutes, and I'm going to pick up part 2 where I go back and do back calculations.